Hello, welcome to the next interesting bit of content from the LibreHub channel. I'm Tobias Wenzel, professor at the Pontificia Universidad Católica de Chile, and today we're going to bring you some really interesting content through our partner organization BINA, that's Bioimaging North America. There we have the world's only work group that's actually focused on builders, on microscope designers and sharers. And so there we also started doing some really cool workshops. And from one of them, we're going to bring you today an interesting piece of presentation from Jeremy Graham about custom scopes. He has built various microscopes during his career, and he's going to share some of the interesting insights. Also, you're going to hear some interesting bits about light sheet microscopy, shared usage, and commercialization. So please enjoy today's seminar.
Okay, so I'll quickly introduce our first speaker. So our first speaker up is Jeremy Graham. So he's had a leading role at Cairn Research for over 20 years, and he very recently started his own company, OpenScopes, to focus on custom microscopy design and support. So Jeremy is very well known in the community for his innovative contributions to many scientific imaging projects, including the open frame microscope. So I'll hand it over to Jeremy now.
Okay, so hi, thanks for the introduction, Gil. I'm Jez Graham, the founder of Custom Scopes, which has been running for about a year and a half now, formerly at Cairn Research. And I'm going to talk to you today briefly about a few projects I've been working on which make use of open source hardware, and the emphasis being on the modularity, the affordability, and the adaptability that I think should be a central theme through open source hardware. So brief introduction to what my interests are and what I'm doing with custom scopes. As Gil mentioned, I'm very heavily involved in the open source microscope platform, working very closely with Imperial College London and still with Cairn Research. And the projects we've been focusing on have been getting microscopes into Africa that can be shipped around the continent and are robust enough for transport and be maintained locally. We've been building microscopes for containment labs where the open source modular nature certainly helps with the long-term support. There's no monolithic unit that needs to be destroyed and removed due to the toxic nature of the labs. Also been working on a few dedicated applications in electrophysiology and cardiac physiology, and building microscopes for startup companies, whereby if they're open source, then when they're ready, they can take the project off in whatever direction they want. In addition to this, I'm very interested in making things cheaper. So I've been working with astronomy, machine vision technology to make predominantly light sources, cameras and filter wheels much more affordable for microscopy, including getting down to the price point where they can serve the amateur microscopy community, which turns out to be quite large. We upgrade existing microscopes to either bring them up to date or to repurpose them for new applications, and do quite a bit of custom build, usually referring to a journal article and helping a biologist to translate some new technique onto their microscope, which will be different probably from what's been published, and working out what's important and how to translate what may have been a breadboard build into a more of a biology-friendly microscope build. So those are things I've been doing. I think it's important to highlight where an open source microscope scores over a traditional and vice versa. So the starting point from a research consultant's point of view is that you're asking more of the researcher. They need to understand, and they need to be interested, and they need to put some effort into the supporting the system themselves, and consultants like me are there to help them. The support will rely on partnership with the group. Generally, the microscope will be less versatile at point of use, so less suitable to core facilities, but more suited to researchers who have specific requirements. So those are a few sort of caveats, but then the advantages are huge. Many optical systems rely on 4F optics, which doesn't lend itself to a regular microscope. You're not limited by any spectral range. You're not limited by particular tube lenses, detectors, ports. You can build as many illumination and detection ports as you like. Solution will tend to be more compact and cheaper, and it will be sustainable beyond support contracts. So there's no fixed term support contract. There's no reason why the system can't be kept running more or less indefinitely. And I think doing things differently in a modular way encourages innovation, because if you have a monolithic platform, the temptation is to reproduce what people have done before. Whereas if you've got a platform that can be put together in any way you like, then it encourages you to explore new things. So the key aspects that I was focused on in this talk is the modularity. So the system should be built up of discrete building blocks. It should allow as much substitution as possible. You shouldn't be tied to a particular component in a particular place. Everything should be individually swappable. And it needs to be serviceable at a component level rather than a system level. Obviously, the researchers putting more effort in themselves, so it needs to be affordable. Part of the key to this is they can allocate the budget where they need it. So if they need a fancy objective or a fancy camera, then they can start with that and then potentially save money on other areas and improve them later on. But it means they can get started. There would typically be a very wide price range for each component, ranging from thousands of dollars to building it yourself for tens or hundreds of dollars. And the costs can be spread out over time, so you can get started and then add functionality as grant funding allows and as your needs progress. It also should be adaptable, so it should be repurposable from a simple wide field system to a confocal or a turf rig, single molecule. Wherever possible, we should adopt standard interfaces, which applies to the microscope itself, but also to fitting in with industry standards such as Thor Labs and the standards of the conventional microscope companies, so that it can accommodate Nikon or Evident components as needed. And basically, the idea is to provide a stable base where you can explore new ideas and take the microscope off in different directions. So to reference these sort of ideas, I'm just going to go through 3 examples of projects I've been involved in recently. First one was to build a custom X-SPIM light sheet on the OpenSPIM model. So doing 2 different magnification of detection, dual-sided illumination. This is a project with Imperial College to build a robust microscope for field studies in Africa, and also like an upgrade progression of a rig that has evolved from being very simple to quite bespoke. So starting with the X-SPIM, obviously the OpenSPIM website you'll be familiar with, probably some of you, and it's very comprehensive. It's got lots of parts. It's got lots of CAD files and models, but it's really not modular at all. So the first thing I did to get to grips with building this for the customer who wanted all this flexibility was to take the model and basically to modularize it. So to break everything down into the individual components so that they can be substituted and changed in the future as required. And alongside the modularity, it's also important, if you've got to go to a lab and make a system work, you've got to be careful about the components. So I sort of thought of this idea of a hierarchy. So you have the easiest things are like the catalogue items that will arrive very quickly, relatively affordable and good information online. You've then got core components that you've got to order from the microscope companies or from camera or laser companies. And then you're always ending up searching a few niche suppliers for things that you have to get from somewhere else. And then alongside the commercially available components, you have self-made, but this also has a hierarchy from 3D printing and DIY, which can be done in days and changed on the fly, versus things that are manually machined or laser cut, which turnaround can be probably a few days and relatively straightforward, versus the things that need making on a 4 or 5 axis machine. You need to get those ordered early and get those done professionally and delivered, and try and get those ones right. The other stuff you can adjust as you go along. And here's some of the components from the OpenSPIM build. So clearly the chambers and the chamber holder, you need to get them machined on at least 4 axis machine and get that done right. Whereas the modular components and setting up the optical rails It's a combination of either 3D printed or machine parts alongside Thor Labs or equivalent optomechanical parts. So that's the Open-SPIM, and basically just making it a bit more modular so that we can change things. This is the microscope that we built for field studies in Africa. So it's very simple. It has a color monochrome camera, nice 4-channel fluorescence illuminator, a quantitative phase illuminator that was completely open source, built at Imperial, and a robust laptop. And it all fits into a robust carry case and can be shipped around Africa. And this has been shipped around a lot already. It was designed to be fully serviceable by the researcher, use predominantly open source components so they can duplicate it at minimal cost, stable, robust, compact, and affordable, and still maintaining all the adaptability if they want to take it into a different direction and do something interesting with it. And as with everything, always maintain a simple substitution of all components so you're not tied to a specific component. And here's some of the images they've got. They've had that for about 6 months now, and it's been shipped around to lots of different countries. And so far, touch wood, it's not broken. And the final example I was going to talk about is an upgrade route of an open frame microscope that started life as a very simple wide field microscope with basic color illumination, an inexpensive camera. It then got upgraded to do 4 channels simultaneously. It then got upgraded to do 4 channels simultaneously and quickly over a large field of view with the kinetics camera. The illumination was not good enough, so we built a critical illuminator with a square fiber, so we can illuminate a quadrant of the camera. Because the image is split over the 4 channels, can illuminate a quadrant of the camera with very flat illumination and high intensity, so they can increase the speed. We actually had to develop a new filter set because of the variation in the wavelengths of multimode lasers to ensure that they could have the 4 colors that they needed. Then had to build a custom layer because they decided they wanted a 5th channel for transmitted light with near infrared. And they also wanted dark field, so we designed a RGB dark field, an NIR illuminator, and wrote micromanager drivers so they can control the illumination for the transmitted light, and also put dark field into any 3 of the 4 fluorescent color channels in a sequential mode. I didn't get involved in the microfluidics, they're the experts on that, so the group were developing the microfluidics themselves alongside. And as they enhanced the microfluidics, everything moved faster. So the final stage was to box up an Arduino so that we could move Micromanager into sequencing mode so they could get rid of the motion artifacts from the fast-moving droplets. So this is all about the adaptability because the microscope's unrecognizable from what started out. And this is the microscope now in its enclosure with advanced microfluidics software and Micromanager running 5-channel imaging. Thank you very much for your attention, and I look forward to maybe any questions at the session at the end.